Thank you very much. I'm not sure whether the microphone is it working? Kind of? Okay, perfect. Okay, yeah, thank you very much for inviting me. I just had a discussion in the coffee corner. I think there is no better place than here to talk about statistical physics. And what I will talk about today is essentially how non-Markovian systems, so how memory effects change the entire game when looking at the motion of colloidal particles when immersed in such systems. So actually, for those people who attended the Venice meeting a couple of weeks ago, you can check your emails. There will be nothing new. For the others, maybe that's a couple of interesting insights here. So let me start by also acknowledging the people. There's a lot of postdocs and PhD students. Some of them have already left. Celia and Ruben are no longer in the group. Ruben has his own group in Mexico. Celia is working industry. And currently Felix, he's heading this subgroup in my institute here. And I should also not forget mention theoretical support from the group of Matthias Krüger at the University of Göttingen, in particular Juliana Kaspers, who is a PhD student in his group. So essentially what I will tell you during the next 45 minutes is how the dynamics, also the equilibrium properties of colloidal particles change when you have as a suspension medium not water, not a purely Newtonian viscous fluid, but if you put them into a viscoelastic medium, which exhibits pronounced memory effects. And I will show you that here using three different settings. The first one is an equilibrium situation, a very old problem, the hopping dynamics over a particle over a potential barrier. Then we will see on what happens if you have a drive. You drive them and then you let them relax. And finally, I will show you what happens if you add self-driven particles to such a viscoelastic fluid. So here just one slide, what distinguishes a viscoelastic fluid from a normal viscous fluid. Well, this is easily seen if you do such a shearing experiment. So you have two plates, you confine some liquid in between, and then if you apply a velocity, a sudden change in velocity, you apply a step-like strain rate to the upper plate, and then you can ask yourself what force is required, what stress is required to make that happen. And in case of a viscous fluid of a Newtonian system, you see that the stress immediately follows the strain rate. That's simply because of the relatively small relaxation times in viscous fluids. However, if you exchange the fluid to a viscoelastic fluid, you see there is a difference here. You have a time-delayed stress response. You have a finite stress relaxation time, which can be easily on the order of a couple of seconds. And the reason is that viscoelastic fluids are typically comprised of, they contain mesoscopic structures, and it just takes a little while for those structures to align to the new shearing conditions. Okay, so this is the system we are using in our experiments. This is a pretty conventional system which has been studied by many people before, in particular on the macroscopic scale. It's an amphiphilic molecule, cetylpyridine chloride. And I mean, like amphiphilic molecules, they form micelles depending on the concentration. And in particular, if you add salt, you increase the attraction between these molecules, which then leads to the formation of rods, which can be pretty long, can be a couple of microns in length, vesicles, and eventually they form what we call a worm-like micellar system, a structure very similar to that of a semi-dilute polymer system. And what's nice about those systems is that on macroscopic scales, it's well known that there is a single relaxation time. That's a little bit different compared to semi-dilute polymer solutions, where the relaxation is, so to say, constrained by a reptation motion, but because these structures, they can break and reform, that makes the relaxation process a little bit more easy. That's one of the reasons why we have chosen that particular system. Okay, now let's come to the first example. This is the hopping dynamics of colloidal particles over a potential barrier. And just as a reminder, I know it's not necessary in that audience, but just keep it as a reference. If you would consider the hopping dynamics of a Brownian particle, an overdamped particle, in a viscous system, then you would obtain here a single time scale, right? Which is, so to say, characterizing the particle dynamics. Now what we are doing, we want to do that now in a viscoelastic system. So how we create such a double well potential? Well, this is something there are different ways to do it. We do it typically by optical means. We have a laser beam which is focused into an objective which is creating a laser spot, and by having a mirror which is periodically moving forward and backward, you can scan the laser beam here, the focus inside the sample plane. And if you synchronize that scanning motion with the intensity, and this is achieved by such a device, an acousto-optical modulator, you can, while scanning, adjust the intensity in such a way that you obtain such a light distribution. And because of optical trapping effects, this then leads to such a double well potential for the particle. So the particle is about 3 microns, and the distance between the two wells is about a micron. So we only talk about a very small particle displacement here. The reason is simply because if you move the potential wells too far away, then the time scales become very large, because these systems are about 10 times as viscous as water. Okay, and here I guess you can see that the particle is really jumping between the two wells. Okay, so here once more, this is the left-right motion. From the probability distribution, you obtain the potential barrier, which the potential shape here, you see very nicely symmetric double well potential. And you can see it's also nicely described by a superposition of a parabolic and a quartic potential. Sure. This is a fit. This is known that for this type, if you scan a Gaussian beam, it's known. This has been shown before. This is a fit. Yes, the orange line is a fit. The symbols are the data. Okay, up to that point, nothing new. Everything is kind of nothing special. But now comes the point. What we measure now is the waiting time distribution. So we measure the time distribution. The particle resides in the left well until it jumps to the right well, and of course also for the right well until it jumps to the left side. This is fully symmetric. And if you plot the probability distribution of these waiting times, you see here 2 decays, 2 time scales. We see a rapid decay and we see a long decay. And that's very different compared to what Clemens told us, because he told us, well, there should be only a single time scale. And in fact, if you would calculate the Clemens result for that condition, you would expect this, this dashed line here. Now, we can very nicely fit, again, actually, thanks for the remark, symbols are always experiments, and solid lines are theory or numerical simulations. You can see now by the solid line that this expression or this data can be nicely fitted by the superposition of 2 exponentials. We have one decay with a short time scale, tau s, and one with a long time scale, tau l. What's even more interesting is to look on how these time scales vary if you change the potential barrier, right? This is something we can easily do in the experiment by changing the light intensity and the scanning conditions. And what you see is, first of all, you see the time scales are clearly separated, right? But what you also see is that only one time scale, the long one, tau l, behaves as predicted by Clemens. It increases exponentially as you increase the potential barrier, while the smaller, the shorter one remains almost unaffected by the potential barrier. You also see that this short time scale is not a small addition to the large one. You see the amplitudes, which are plotted here, the relative amplitudes are essentially of the same order of magnitude. Now, to understand that, we came up with the following simple model. We consider the colloidal particle as the tracer particle because we can trace its motion. And this particle is interacting with the double well potential. That's clear. And now to consider the interaction between this tracer particle with the viscoelastic fluid, we have added a bath particle. We consider a bath particle which has its own friction coefficient gamma b and which is connected with a linear spring with stiffness kappa b to the tracer particle. And this should remind you very much to the Maxwell model, which is known to be a good description for many viscoelastic materials. But here, this corresponds now to the microscopic version of it. And the advantage of this description is that you can immediately obtain two equations of motion to describe then the motion of the tracer particle. The tracer particle is interacting with the bath particle, interacting with the double well potential. Here we have some noise. And the bath particle is only interacting with the tracer particle because it only captures the properties of the viscoelastic fluid. Yeah, that's a good point. I mean, first of all, I would say it's from a theoretical point of view, it's the simplest model, as you will see in a second, or which is describing our experiments. We don't have a full microscopic understanding. Maybe if you give me a little bit of time later, I will show you, because later we will also add another bath particle. We have an idea how to link that microscopically to what's happening inside that systems. But here, just take it as a formal approach, which is kind of replicating the Maxwell model, right? I mean, it's clear you have some elasticity. You will see also this is leading to a memory effect, but just take it as a formal description here. Okay, so we have these two equations of motions. Sure. Yes, I will show you. Actually, it's large. It has a higher friction coefficient. That's not my point. I mean, we have now different open parameters. We have the stiffness here. We have the friction coefficients. And in order to obtain no values for that, I think that's your question, we can fit that model to the probability distribution, to the mean square displacement. And when we do that, then we exactly obtain the properties here, the friction coefficient of the tracer particle, of the bath particle, the spring constant. And from that, and that's now important, you immediately see that the relaxation time of the bath particle is about 7 times as large as that of the tracer particle, which means that the tracer is faster than the bath particle, which also means if the tracer moves fast, it will not be in equilibrium with the bath particle. And this is exactly what we need to have a memory effect in that system. Now with that model, we can, and these are actually, yeah, exactly. We fit, absolutely. We fit it to the probability distribution, to the mean square displacement, and then we obtain the fitting parameters, which have not been determined before. And this is what is now important. And once having these fitting parameters, of course, and using that equations, we can now also calculate what we have measured before, the probability distribution of the waiting time. And you see, and this is in fact now here, the orange line, which very nicely agree with our experimental data. You also see this also applies to the time constants, to the behavior of the time constants, and also to the amplitudes. Now, the question is there a simple way, because we have been puzzled, it's a little bit strange to have these two time constants. In particular, the question is why one of these times, of these decays of the waiting time distribution is independent of the potential barrier height, which is very different compared to the Kramer's prediction. And that's a simple way to understand it. Let's assume we start in a fully equilibrated system. Let's assume the tracer particle is sitting in, let's say, the left potential well for quite some time, okay? And then, of course, in the meantime, also the bath particle, which has a longer relaxation time, can fully relax. So there is no elastic energy stored in the spring. Now, the tracer particle is making a thermally assisted jump over the potential barrier. And because the friction of the bath particle, as I showed you, is much larger than that of the tracer, let's for simplicity assume it's infinitely large, so it would stay at its original position. You see the spring is loaded, and so that means we have now some elastic energy in the system, which is leading here to a deformation of the effective potential. And now you see what happens. Now, of course, the particle can very easily and on a very short time scale move back. So this is actually then the reason for this fast time scale in the waiting time probability distribution. And you also now understand immediately why this short time scale is pretty independent of the potential barrier, because the particle is not even probing the potential barrier. It's more or less by the elastic energy pulled back to the left side again. This is only one possibility. The particle can, of course, also has the chance to relax down. And if this is happening, this takes quite some time. In the meantime, also the bath particle can relax. And if now the particle wants to do another jump, you see all the elastic energy has decayed, has been relaxed. The only energy source is the thermal energy, and that's the reason in this hand-waving argument why the long time scale follows pretty much this Kramer's type relationship here. Exactly. The bath particle, that's very important. That's what I also like. It's really, you can clearly separate it. The bath particle is only mimicking the properties of the surrounding fluid. It's completely independent. Yeah. Absolutely, absolutely. You can also do it for compression. It works the same, right? It could also, you could also put it on that side, right? But and then the spring is compressed, but then it would also make it works on both sides actually. Yeah. Okay. Well. For an asymmetric. Okay, it's getting more complex. Yeah. I mean, it would not be we have not tested it, but I would expect the model also to remain valid. We have never tried that. Yeah. We can also do that experimentally. That's not an issue here. Okay, because of these memory effects, it's clear that now our effective potential becomes time dependent. So if you have a fully Markovian system, so the force acting on a particle is just given by the probability distribution that the particle initially at position X is making a displacement by L within the time increment delta t, then you multiply it with the velocity and the friction coefficient, and you obtain the force. From that, you obtain the potential. But of course, now we have to consider also where the particle has been prior to time t equals 0. We have to know the position at time minus t. So we need a 3-point conditional probability, which of course then leads to an effective potential. It also depends on the time. And this is something we can directly measure because we can measure these probability distributions here. This is the data. Again, the open symbols are the experimental data, assuming that the particle has been located at the left potential well, and if this initial condition is infinitely in the past, of course, we fully recover the double well potential, the symmetric double well potential, because then all memory effects have been decayed. However, if we now move this initial constraint more and more to the presence, you see minus 30 seconds, 10, 3, 1, you see clearly this effective asymmetric potential I have just shown you in the cartoon before. What we found interesting is that even if the initial condition here, if you look at this kind of brownish curve here, here the initial condition has been put minus 30 seconds into the past, you clearly see this asymmetric double well potential. We found it interesting because the stress relaxation time in such system is only on the order of about 2 seconds. And you see that in presence of a potential barrier, such memory effects can last pretty long. And as a kind of a clue why this long memory effects come into play, we considered the positional correlation function between the bath particle and the tracer particle. And you see this first increases, and only at the time scale of the long time scale here, tau L, which is on the order of about 100 seconds, it decays. And this is actually the reason why the memory effects in that setting here survive so long. So I just have to check my talk is till 10:30. Yes. Okay. Yep. Yep. Okay. There's actually a simple way to test this idea by first localizing the tracer particle in a very stiff trap, okay, and we keep it there for 100 seconds for quite some time, and then suddenly, we change the potential to a double well potential. So this protocol ensures that we first prepare the system in a fully equilibrated state where everything has been relaxed. And now we can independently measure the probability distribution for the first jump and then for the second jump, okay? So the first jump starts from a fully equilibrated system, and according to our expectation, we would expect that this preferentially contains then the large timescales, and this is exactly what we find here. These are the accumulated waiting times, and you see for the first barrier crossing events, the short timescales are pretty much missing, and after the second jump, we have more or less fully recovered that case we would have for an unconstrained hopping event. Okay, this is also in support that this relaxation time, that the effective relaxation time is on the order of tau L. Okay, so far this was in equilibrium, and now I want to show you what changes if you go into non-equilibrium. And we do that by having now replacing the double well potential with a single stiff optical trap, and we move now the particle much larger, much further than before. I mean, before we had a particle motion on the order of a micron, a third of a particle diameter. Now we move the particle 20, 30 microns with a constant velocity with a trap, and then we turn off the trap. And now the particle, of course, is relaxing back because you have accumulated strain, right? Like you also macroscopically, I move in this direction, I accumulate strain, and then eventually I'm recoiling back. And this is exactly how it looks in the experiment. This is, note, this is the co-moving frame of the optical trap. So let's see. So here now we are shearing, and then we turn the trap off, and then you see this recoil, right? And now we can do thousands of that curves. You need a lot of statistics to have good averages. And if you do that, this is what you obtain here, the colored curve in the background. These are the single trajectories. These are these recoils. And the mean, these are, again, the open symbols in the back are shown here. And what you find is that they can be very well described by a superposition, again, of two timescales, which are, of course, not related to the probability distribution of the waiting times. But you see, again, we have a double exponential recoil. We have a short time scale. We have a long time scale. We can also vary the velocity. We move this trap here. And when we do that, we can plot here the amplitudes, and you see the amplitudes increase in a linear fashion depending on the shearing velocity. And again, you can ask yourself, what's the simplest model to explain that? Clearly, a single bath particle is not sufficient to lead to a double exponential recoil curve. That would only give you one time scale. Okay, we just have to add another bath particle. And so this is the model. This is the simplest model we came up with. We have here our tracer particle. We have here two bath particles. You can also connect them on the same side. That leads to the same results. Each of them has its own friction coefficient. each of them has its own spring constant. The fact that the amplitudes increase linear means it must be a linear model, right? Otherwise, this would not explain why the amplitudes increase in such a way. Again, we obtain now three equations of motion. This one is for the tracer particle. The first term is the interaction with the optical potential. This is the trap stiffness of the optical tweezer. It depends now on time because it can be on during the shearing and can be 0 during the recoil. And here, this is the interaction with the two adjacent bath particles. And now we have for each of the bath particles one equation of motion where you only consider the interaction with the tracer particle. And indeed, if you turn the optical trap off, this is exactly that's then the situation which describes the recoil. We obtain from that equations here two time scales, which are exactly leading then to such agreement. Here you see the time scales. Actually, you see I also have plotted for the different velocities, the shearing velocity, the time scales. The time scales remain identical. They are independent of V, and those time scales are actually immediately extracted from these equations here. Now, even though that model looks very simple, it's quite complex because we have two different kind of force conditions. When the optical trap is turned off, then the total forces acting between the particles, between all three particles, sums up to 0, right? We have a fully reciprocal conditions, and this led to the two time scales I just showed you in this inset here. During the shear, however, when you shear the particle, and if you consider the situation from the co-moving frame of the tracer particle, then of course, the total forces acting on these particles are no longer in equilibrium. They are no longer sum up to 0, right? So if you fix that here during the shearing, these two particles are fully decoupled, and this leads now to non-reciprocal conditions. And this is also something you can immediately extract from this model, and these are now the other time scales which are relevant under non-reciprocal conditions. So these are the time scales which are relevant during the shearing itself. And to experimentally measure these time scales, we have varied the shearing times, right? During the shear, we are in the situation that the optical trap is on. So we have then these two time scales which should be relevant. And in fact here, the agreement between the experimental data and the theoretical descriptions are now achieved here with this expression, which is an immediate result actually of this set of differential equations, which now contains here the tilde time scales, which correspond here to these non-reciprocal conditions. This kind of model is very robust, actually. We tried to trick it a little bit. We also added a modification. I have shown you before we were dragging the particle and then immediately releasing it, right? Now what we have done is we have dragged it, kept the trap on for some time, a waiting time, and only then released it, okay? And even if we do that, you see we have reasonable agreement between the theory and the numerical simulations in our experimental data. And we can also now only from the numerical simulations obtain the elastic energy imposed into the system, so which is just the elastic energy between the tracer particle and the bath particle. And you clearly see here, for example, and looking here at that blue curve, which corresponds to the elastic energy of one particle, during the waiting time, where these non-reciprocal time scales occur, which are longer, the elastic energies decays only slowly. Then here, after we release the trap, we have here a sudden decay. And this actually shows you how complex this relaxation of elastic energies is. You can even have here non-monotonic changes. You can also have a situation where here the elastic energy of one bath particle is first decaying, then partially recovering, and then fully decaying. We also have tested this two bath particle model with equilibrium situations, and you also see this is the mean square displacement, again experimental data as bullets, with the result of our numerical simulation. You see it nicely agrees, right? We see here this typical nonlinear slope that's very characteristic for viscoelastic systems, and you see here this is now repeated for different concentrations where we obtain a kind of a glass-like behavior with a plateau. And this now brings me back to the question you asked before, what's the microscopic, so to say, motivation for that model? And what we have done here is we have now measured the spring constants and the friction coefficient of the two bath particles as a function of the concentration of our micellar system. And what you see is the properties of one bath particle hardly vary with the concentration, while the other one, the properties, the friction and the spring coefficient here of the other bath particle strongly vary. And our current interpretation is that one of the bath particles, this one here, probes more the response at small particle displacements, which do not change so much on the concentration of the micellar system, while the other one is more probing the response to larger shearing distances, right? And this would also explain why in case of this double well potential, where the particle was hardly moving its own particle diameter, a single bath particle model was sufficient. Okay, so in the last couple of minutes, I would like to briefly address the last situation. What happens if you add a active particle, a self-driven particle, to a viscoelastic fluid? This here is now a slightly different system, but and this is our self-driven particle. How we make these particles self-propelled, maybe if you are interested, I can tell you later. But let me just play you a movie. And you can see it's tenfold accelerated. So this entire movie covers maybe half an hour or so. And what you see during this half hour, that the particle substantially changes its orientation, right? And this is surprising because if you would calculate the rotational diffusion timescale, depending on the for that viscosity, this would lead to about 50,000 seconds, which is 15 hours. So normally you would expect that this particle during half an hour is essentially maintaining its direction of motion. And you see clear deviations. And this is even, you can also see that this effect becomes even stronger and stronger if you increase the propulsion velocity here. The more you increase the propulsion velocity, the more the particle starts to change its orientational direction. And actually what you can do now, you can measure the angular diffusion coefficient at sufficiently large times. It becomes linear. From that you can obtain the rotational diffusion coefficient. And if you plot now the rotational diffusion coefficient normalized to that you measure for a passive particle as a function of the Weissenberg number, this is essentially the propulsion velocity. You see here an enhancement of more than 2 orders of magnitude, right? This is a very, very strong effect. And this effect is not only shown in that system, this effect is also found in other viscoelastic systems. This here is a glassy background, so where the viscoelasticity is made by having a binary suspension of colloidal particles. They form a glass. Actually, if you look here at the mean square displacement, you see that above a area fraction of about 0.776, in a glassy state. And if you now add to such a viscoelastic system a active particle, I mean here this is the velocity, the propulsion velocity is 0. It's pretty much trapped, right? With the arrows you see the orientational changes. It's pretty much confined. If you now, this is actually at an area fraction of 0.73, which is below the glass transition. If you now make it self-propelled. Of course, not surprising, the particle starts to move. But what's now interesting is if we have the same propulsion velocity, but increase the area fraction, we now go from here to here closer to the glass transition, you see that the orientational dynamics becomes much faster. Right? You see that here from these arrows, this particle almost turns by 130 degrees within the time. This is the same time scale here. It only maybe changes its orientation by 90 degrees. So we have here a similar effect. And in fact, what you can do now, you can measure the angular mean square displacement as a function of the area fraction. And what you see is for that area fraction, the green data, which correspond to the glass transition, the rotational dynamics is fastest. From this value, you can then obtain the rotational diffusion coefficient, and this looks like that. It peaks at the glass transition. There's an enhancement of maybe a factor of 25. Yeah? And this effect, again, is entirely absent if you have a Brownian particle. So it's only caused by, you need both things. You need a viscoelastic fluid and you need an active particle. If you do the same experiment for a Brownian particle, you see there is hardly any area fraction dependence, and the rotational relaxation, rotational time, rotational diffusion time essentially always remains at the same value. Now, how to understand that? Now consider these active particles to have a self-propulsion velocity, a swimming velocity, which is new, and the orientation, this is a unit vector, is described by u, okay? And if you now consider the drag force of such a particle in a viscous fluid, this is of course simply given by the Stokes expression, minus 6p viscosity particle diameter times the true particle velocity. And the propulsion velocity, of course, is pointing in the other direction, which is just given by 6 pi eta a, and here is now the propulsion velocity. Okay, this is what you immediately can write down. If you translate that now to viscoelastic fluids, the viscosity has to be replaced by this memory kernel, which is connected to a stress relaxation modulus. And so you obtain exactly the same types of equation here. But now with memory compared to here. What has to hold in both equations is that the self-propelled motion is a force-free process. So all the drag force, the propulsion force, and the noise always have to add up to 0. This is a general statement you can always make when considering self-propulsion. That means apart from noise, you can always say that the drag force is parallel to minus the propulsion force. And this is actually true here. Here the drag force, if I move in this direction in a Newtonian fluid, the drag force is always pointing in the opposite direction. And this is no longer true if you have memory in that system, right? Because now the particle orientation at time t depends on the accumulated history, which now means that the drag force is no longer antiparallel to the particle direction of motion. And the consequence of that is that we formally can assign a torque acting on the particle, right? Assume you move in this direction, but the drag force is pointing here in this direction. We can say this is similar like having a torque acting on the particle, and this torque, there's a lever arm, mu is a parameter, this is a fitting parameter, which is on the order of 1. A is the particle diameter, u is the orientation of the particle, and this is here cross the drag force. This leads to a time-dependent torque on the particle. And this time-dependent torque, if you add that to the equation of motion for the rotational dynamics, this then leads exactly to such a peak here. You have to consider the right estimates for the stress relaxation modulus. They are known for colloidal systems. And this is, so to say, the reason why we have here such a non-monotonic behavior. The system, the rotational diffusion coefficient peaks right at that position where the relaxation time becomes largest, and this is exactly what happens at the glass transition. So I like that cartoon, actually, which summarizes this last aspect very much. This is a suggestion from Celia Lozano, and she said, well, the situation is a little bit similar, like if you have a blind driver. I mean, never do that. You have a blind driver and you have a co-pilot, and there is a windy road, and the co-pilot always gives you direction, turn to the left, turn to the right, and maybe this is an older driver, maybe the hearing capabilities are a little bit degrading, so there's a kind of a time delay, and you immediately understand that this leads then to such a curve, right? And this is essentially, if I sum it up, this I would say this is essentially the physics behind this enhancement here. Because of the time delay, you are not immediately your flow. The flow field around the active particle is not that instantaneously created, which then leads to this torque here. I should also mention that we have very recently confirmed this effect also for rod-like suspensions, where we also see here such a maximum. So it seems to be very generic. And this is actually my summary. I think I don't have to read it off. Again, I think all what I wanted to show you, going to viscoelastic fluids, even if you are in the linear rheological regime. So we are not making use of shear thinning or shear thickening. Might be that's the first thing which comes to your mind when thinking about those systems, but the pure presence of a memory effect is changing equilibrium properties, the transient relaxation, but also the motion of active particles in such systems. Thank you very much.